Please note that this is a sponsored event, and any opinions expressed are those of the presenters and do not necessarily reflect the views of ASCE. ASCE also asks that presenters and participants refrain from discussions surrounding competitors and pricings of products and services. And without further delay, welcome to Flow and Hydraulics. This is the second webinar in the 2024 series of 4 provided by the Alliance for PE Pipe, WL Plastics, and Core in Maine. Each of the webinars in 2024 series are 75 minutes. And now it is my pleasure to welcome back for the 4th year providing valuable HDPE sponsored webinars with ASCE, Alan Ambler. Welcome back, Alan.
Hey, Robin, thank you so very much. We're so happy that everybody is here joining us. We've got quite a crowd coming through, and we've got quite a lot of support to try to help answer all of those questions as we go through. So what happens with the Alliance for PE Pipe webinars are any question that you may very well have right then and there, just go type it directly into the Q&A, and we have a bench support to be able to help answer that question. It doesn't have to be pertaining to flow and hydraulics in any way. Just make sure you type that question in, and we've got a team of strong experts to be able to back you up here. So today's presentation is on flow and hydraulics. The Alliance for PE Pipe is a nonprofit that focuses on educational events like this aimed at teaching civil engineers, operators, and other people within the municipal water and wastewater market how to integrate HDPE into their system, or just generally try to improve infrastructure. So these members contribute to the Alliance for PE Pipe to be able to accelerate that program and bring you that education that we really need to help advance infrastructure. If you like HDPE pipe and you want to know what we're doing for social media, we have all of these standard social media applications and post every day. Lots of things going on in the country with regard to high-density polyethylene installation. If you just want to see projects in your area or local part of the country, we've got some that are going on in that area as well. These are some of the upcoming shows that we've got. There's, in addition to the webinar program, we also have a road show program, in which case we bring 10,000 pounds worth of gear in a Penske truck for you to be able to touch and feel and see live demonstrations of that HDPE part and piece for you as well. Those same experts are out there coming to your town with this truck and all of this service, and it's a great way to be able to sit through some training to be able to learn about HDPE and how to use that part and piece as well. Another free resource that the Alliance for PE Pipe offers happens to be seminars. We do conduct quite a few seminars every year to look at your project specifics or just your engineering group or your municipality itself, and we'll put you in direct contact with a whole lot of experts in order to be able to answer your question and perform a project review for you. We also do have a very robust amount of specifications on our website at pepipe.org that you can certainly download, that covers horizontal directional drill, pipe bursting, open cut, all things to do with HDPE as well. We do have the engineers package on there. The specifications are updated for 2023. We're also updating the remainder of this engineers package that includes things like Insider's Guide to the Vocabulary, PPI's Handbook on Polyethylene Pipe, and a whole lot more. Also includes standard details. Those are available in both PDF and AutoCAD format for you, and case studies. So oftentimes we don't like to be the first one to do something. And let me tell you, we've got a lot of projects that have included HDPE previously, and then here are the resources there for you to be able to see in your area. One of the things that the Alliance has done is worked with Engineers Without Borders. HDPE pipe is a perfectly good pipe use for above ground installation to try to bring water to remote village that currently has to carry their water from the water source. So please, if you feel like donating to a good cause with Engineers Without Borders, this is the Washington, D.C. office. The Alliance doesn't get any of the money from this. We want you to direct donate directly to the cause. We have coordinated with our members to donate pipe, fittings, materials, and all sorts of things, and looking for an installation here this year in 2024. Here's our presenters today and all the contact list and information that we have. So if you want to take a screenshot of the screen and send any one of these people an email, their volunteer efforts really helped make today's presentation possible. And we're extremely benefited by them sharing their knowledge and experience. Here's a list of acknowledgments of where we got the information to be able to provide you with detailed information today. And that's what we always try to do is quote exactly where we got the information. So, Rusty, you want to come on and talk to us a little bit about Core and Main? We have sponsors to be able to help make sure that we can bring you this education and information. And here's Rusty Reeves.
You bet. Hey, thanks, Alan. Yeah, Core and Main, we're a national waterworks infrastructure supplier. I mean, we distribute anything, piping, valves, fittings, pumps, metering, any type of thing you need for utilities. We love getting involved with the PE Alliance and ASCE on these webinars just to really get the word out there for polyethylene piping systems. And, we can take care of anything, support you in any way, whether it's fusion equipment, either sales or rental, technicians, or training your technicians to be able to fuse the pipe together. And always happy to look at your projects, help with kind of value engineering, whether it be for fabrications or, cost-effective savings that we can help you with. So, again, please feel free to contact us and enjoy the webinar. Thanks, Alan.
Awesome. Richard, come on and tell us about WL Plastics as well.
Hello, everybody. Welcome to this seminar. I think it's going to be a very, very exciting one. WL Plastics, we're one of the largest polyethylene pipe manufacturers in North America. We do sell internationally as well, but as Rusty said, Core and Main is a significant part of our value chain. I mean, we work together, them as a distributor and us as a manufacturer. And then, of course, we have the manufacturing side on the polyethylene side as well. So with Ineos Group. We've been in this manufacturing situation since 2000. We're happy to sponsor these events because we believe they're very educational. This one we're really excited about. It's been a hot topic for many years, and there's some really great experts here to help us better understand what actually happens in our infrastructure situation. So I'm looking really forward to it. And again, I'd like to thank ASCE and the PE Alliance for putting this together.
Awesome. Richard, thank you so very much. Here's our speakers today. Emily Walton, if you'd like to come on. Matt and Dusty, please come on. They're going to share their personal experiences with us from Metropolitan Utility District, actually working with a hydraulic model in that manner. Matt did a hydraulic model for me while I was his client at the city of Castleberry many years ago. We worked together fairly well to be able to put that model together. And then Dusty is going to talk generally about some properties of HDPE. You guys want to introduce yourself? Emily first.
Yes, so I work for the Metropolitan Utilities District here in Omaha, Nebraska. We serve eastern Nebraska as their water utility.
Awesome. Matt?
Yeah, thanks, Alan. Matt Gurry. I'm a licensed civil engineer and somehow got trapped in the world of software sales. So, spent a lot of time in my engineering consulting days evaluating hydraulic models and dealing with piping and happy to be here and share what I know with you guys.
Awesome. Dusty?
Yeah, Dustin Langston with WL Plastics, 18 years, 19 years, I guess, this year with WL Plastics and HDPE pipe, and currently VP of Engineering and Quality Assurance. And like Alan said, I'll be doing the pipe portion of this, the HDPE pipe section.
Okay, and we have a bench as well. So we're just going to recognize Stephen Boros, Dan Landy, and of course, Peter Dyke on the bench for us in that manner. So they're going to be answering your questions. We've already gotten some questions right away. So that's perfect. Everybody out there, that's exactly how this webinar works. You type in whatever questions on the top of your mind, and we've got these experts to be able to help push that along and bring you an answer to that question. So bench, thank you so much for your effort. Today's topics essentially are properties of HDPE, a subset of what we call the 301, ID matching, hydraulic modeling, and using a hydraulic model for system operation analysis. So once you get that model developed, we want to be able to use it to just to give us some insight about how that system operates. Got to calibrate that field model in order to be able to have it give us good, accurate information in different ways, and then direct field results of replacing aged metallic pipes that have suffered from tuberculation and reduced flow. So Emily's definitely got a great story to share with us for actual application for it as well. So Dusty, here's the material. Go ahead and take it away.
Awesome. Thanks so much. Oftentimes in the water side of things, HDPE pipe gets referred to as kind of the new kid on the block. We've been around for a very long time, just as long as PVC, and we're very, very heavily involved in a lot of other markets outside of water and sewer. So I can understand the new kid on the block mentality, but we have been around for a very, very long time. Next slide, please. So this is the whole magic of HDPE pipe. It is a thermoplastic material, which it means it can be melted back down to its base and reformed and put back into a new shape, or in this particular case, what you're seeing here, which looks like it might have frozen, Alan, and there we go. It makes the product fusible. HDPE pipe PE4710 is a fully fusible, weldable product. And that right there was the final sequence that you just got to witness of a thermal butt fusion. So we're going to take the pipe ends, we're going to shape them down, we're going to heat it up and then press it together at 400 degrees Fahrenheit, which is the melting temperature of the material. Next slide. And the reason this is possible is because HDPE pipe is a semi-crystalline polymer. It has regions of crystalline structure, and then it also has amorphous regions. And this really makes for the best of both worlds, where you have a very strong material, high pressure ratings, things like that. But then you also have an amorphous pipe, or the amorphous regions help with ductility of the pipe. And so you have a very good balance between strong yet flexible. Go ahead, next slide. But with that comes a little bit of a different mentality in how you think about plastic pipe. This is PVC and HDPE, both all plastic materials really, stress over time. So it's not like a metallic where you have a tensile strength and then you take, a safety factor of some kind. You need to understand that with all plastics, you're going to have strength over time. And so when you're doing a burial design, for example, you'll use the apparent elastic modulus for the length of the time that it's being installed. So the 50-year, 100-year modulus, which is 29,000 PSI. Now, if you're taking very, very short stresses, then you take a higher modulus. For example, instantaneous, we'll get into that in the surge portion of this presentation, but then you'll take that 150,000 PSI modulus. So just keep that in mind. Time versus stress for polyethylene and all plastics, you need to keep that in mind. Alan.
So, Dusty, just to for everybody out there, when that pipe is installed in an open trench condition and the soil that surrounds that pipe, it works together with a pipe stiffness and soil stiffness factor that after installation, there's no more load on that pipe itself. So that's not a stress scenario once it's been installed, just to elaborate.
Once that's buried and especially compacted, you have soil arching that actually takes the load of everything above it. But yeah, thank you very much for that, Alan. Go ahead, next slide. So what is PE4710? PE4710, if you go to order polyethylene pipe, that is going to be the designation, the material designation that you'll be ordering. We have, again, model specs that Alan talked about before. All those model specs call out PE4710. PE stands for polyethylene. The 4 is the density range. 7 is the slow crack growth resistance, or the PINT test value. And then 10 is the hydrostatic design stress. Every material out there now for pressure rated is PE 4710. You might still see some older specs from the early 90s that might call out a PE 3408, for example, but those materials aren't really commercially available anymore. Everything today is PE 4710. I love this slide. It lets me nerd out. Everybody in the plastic industry has a job because of the knowledge of this graph. If we didn't understand this, we really wouldn't understand plastics and pressure applications. So this is developed and submitted to the Plastic Pipe Institute, this data on all plastic materials for pressure. So this is not just polyethylene, this is also for PVC pipe. And so we're going to understand, hey, if we put pressure inside of this, the piping product, and over a long period of time, what is that going to do to the material? So if you were to, the tensile strength, for example, for polyethylene, 4710 is 3,500 PSI. If you were to put 3,500 PSI of hoop stress on that product, you'd get a very quick failure. And so we need to figure out, at what point in the very long future can we put pressure in this pipe and just not have a failure? We're saying 100-year life on this pipe. It's well past 100 years, but we need to find that point. And that's what this graph is, the long-term hydrostatic strength, or the HDB, hydrostatic design basis of the material. And so for HDPE pipe, for your pressure rating, no, go ahead, Alan, next slide. We're using 1,000 PSI. So here's the pressure rating formula. And we're going to take the data from the last graph, and we're going to insert it into this equation for the HDS is 1,000 PSI. And we're going to figure out the pressure rating of every DR pipe. Every DR pipe does have a pressure rating that goes along with it. Your most common are going to be like DR11, for example, rated at 200 PSI, DR17 rated at 125 PSI. And those are working pressures. That is what we advertise that pipe to be run at. There's no need for an additional safety factor, and DR11s are often run at 100 PSI or less. That's definitely overkill. But this is the exact equation you would use to figure out what the pressure rating of your project would be. I will talk a little bit more about temperature, though. I do want to mention anything above 80 degrees Fahrenheit, you start derating the pressure of the pipe. So if you have an above ground application that's going to be out in the sun in the summer, and that pipe's 120 degrees, you use a 30% pressure deration. And you can get that from this chart or from the Plastic Pipe Institute handbook. Perfect. Now to the next one. And we're going to talk about this a lot today. Surge and surge analysis in HDPE pipe. It definitely acts differently than any other pipe material that you're used to designing with. HDPE pipe with that lower elastic modulus than our competition acts as a giant shock absorber. And so you actually get less surge in HDPE pipe than other piping materials. The other big difference between our material and others, you're allowed a 2 times pressure rating for occasional surges. So a DR11, 200 PSI pipe can surge up to 400 PSI. And then for recurring surges, several surges a minute, it's a 1.5 times multiplier. So that DR11, 200 PSI pipe would be rated at 300 PSI. DR7 is pretty extreme in this case. That's rated at 335 for working pressure, constant pressure, and can occasionally surge up to 670 PSI. So very, very high pressures allowed. So what is surge pressure? Surge pressure happens when you have a velocity change inside of a pipeline. So if you, for fire flows are by far one of the worst scenarios that you'll come across. So you have a very, very fast moving water column, and then all of a sudden the pumps are turned off on the fire truck, or a valve is closed, or even, if you're working with other pipe materials, if something were to clog the line and stop flow during a high velocity occurrence, you have a pressure surge. You have a water hammer event. And these pressure surges are not just one direction. They actually reflect back through that pipeline. And so with HDPE pipe, again, that lower elastic modulus, we're going to reduce that hammer, that water hammer, through the pipeline. Go ahead, next. So 2 factors ultimately affect surge. So velocity change, and even more specifically, if you really get into the tiny little bits of it, how fast that valve turns on and off. you can get to, very, very fast close times, and that'll actually give you a higher amplitude. But then again, the elastic modulus of that material. Polyethylene pipe uses 150,000 PSI, PVC uses 400,000 PSI, and ductile iron uses 24 million PSI. So that results, if I have my camera covering it, but you get a much higher surge in a ductile iron pipe at just 5 feet per second than you would in a polyethylene pipe. Alan.
Yeah, so that's the exact summary that I was coming on to say. So Dusty, yeah, absolutely. So the HDP itself can act as an attenuator in some areas to be able to resist that surge, and that's that viscoelastic behavior that we talked about. So you're hitting on all the parts, Dusty. Way to go!
Excellent. I think I've just got one more slide on surge. Next slide. So this is just graphical. Us versus the competition, how you actually design for surge of, again, polyethylene versus ductile iron versus PVC. So for HDPE pipe, again, occasional surge, 2 times the pressure class, 1.5 times for recurring. PVC is a 1.6 for occasional and a 1.0 for recurring. And then ductile iron is just the pressure class plus 100 PSI, which, as you saw on the previous slide, a 5 foot per second gets you well into the, above the pressure rating for a ductile iron pipe. And then fatigue resistance. So, not only do we reduce the magnitude, the pressure of these surge events, HDPE pipe is so flexible that it's not bothered by fatigue. Fatigue is actually not a design consideration for HDPE pipe. You don't really have to worry about it and figuring out how many cycles it can handle. For example, the University of Texas Arlington did a test on DR17 125 PSI rated pipe, where they took it past 15 million cycles at 2 times the pressure rating and had no failures. My favorite part of that test they did is Harvey Svetlik. He supplied the pipe material for that testing. And after the pipe material was taken off test, 15 million cycles, they actually tested it for new pipe properties, and it passed all the tests for a brand new pipe. So again, fatigue is not really something we're worried about with HDPE pipe.
So in addition to the failure mechanisms, over insertion or over deflection of a bell and spigot joint can also provide some installation problems that plague bell and spigot pipe systems. But just like everything, we want to know how to install it. There are a few other things to do with HDPE, which is why we do this educational component, and we want you to be successful in your installation. This was just a small subset itself of our 301 program. Dusty can spend an hour and a half talking about that, all 301 itself and all the installation things, and definitely check out our YouTube channel for more. So certainly send us questions now. We're going to move on to the ID matching portion of this. In our industry, in our field, we often get pointed questions about the smaller ID of the pipeline, the HDPE pipeline, because you need a thicker pipe wall to be able to provide that pressure service. So there's a couple of different ways to be able to look at this. One of the most simplified methods really happens to be looking at simple pipe, just the length of the pipe and one pump into it. But in reality, that's not how networks and pipe networks really work. So here's just an example of a calculation of just pure head loss across a certain simple one pipe solution, 10,000 feet long, 24-inch pipe, a defined flow, and then defined head loss through that. If you wanted to, you can look at obviously DR13.5 as opposed to DR11 in some municipal networks, is because most don't operate at 200 PSI. They're more in the 55 to 70 range, if that gives you some pause. But over time, the inside of a metallic pipe is going to decrease in its friction loss, but the plastic pipes simply won't decrease in that time period. So the bulk and bevy of this presentation is to bring you information about hydraulic modeling, why it's necessary, and how some that can really be only the way to estimate your friction. friction loss throughout the pipe, especially when we got complicated systems. This slide is set up to show you an old pipe table that the fittings that are necessary to be able to operate, isolate the system, give a equivalent friction loss of certain pipe lengths as we go through to it. So the older pipe tables here will show you some of these. Obviously now computer modeling gives us a great tool in order to be able to develop that hydraulic model and actually look at the actual pipe materials and the size of the pipe through this. Here's just a good example of taking that pipe size and the impact of the fitting through that. So it's simply not just one theoretical length of pipe with no connections, no appurtenances through that. As you can see here, for a 6-inch pipe, a globe valve, if it's fully open, adds 172 feet of equivalent head loss along that pipe. So we have certainly a whole lot of things to be able to consider when looking at head loss through these fittings as we see them. Okay, so that's just a small little bit before we get right into Matt. Matt, come on in, tell us about what hydraulic modeling is, and then we'll go to the calibration side. Glad you're here.
Sure, absolutely. Pleasure to be with you all this afternoon. Everybody thinks kind of hydraulic modeling is this black box, and realistically, it's just a bunch of calculations that is taking place. And one of the big things I always like to point out is if you don't have very good information coming in, you're not going to have very good information coming out. So garbage in, garbage out, making sure you understand that. But ultimately, it's not a black box. Next slide, Alan. It is simply nothing more than a bunch of equations put in place. Whether it's Hayes and Williams or Darcy-Weibach or Reynolds numbers, there's pressure loss equations. There's a lot of different equations that are being done to manually be calculated, and that's the simplicity of it, to have us focus on being able to structure what we need to. We've got free discharge, which represents hydrants or tanks, and how water leaves and enters the distribution system under pressure in those applications. Next slide. And then ultimately you have the Hardy Cross, right, where it allows you to understand how the water is flowing within the network. Just to do one loop, with just hand calculations would probably take me a day, and I'd be exhausted and ready to call it a day after that, right? So being able to do large networks is very complex. The model's there to simplify it, right? And allows us to, and with this, you get a better understanding of flow direction, looking at individual pipe sections, understanding what are the conditions and constraints that you're really trying to design and understand about that particular application and need. What a lot of people don't realize is the Hardy Cross method was developed back in 1930, and computers started in around the 1960s, and then really with more powerful PCs in the early 90s, modeling really started to take off, and we were able to do more computation and a better understanding of kind of where things are. And with that, our understanding of being able to do a diagnostics in the next steps is really powerful. But I think a lot of people don't realize how long ago modeling actually started and how long it's been around. And it's not this black box or something that's new. It's proven. It's using the existing equations that have been done for decades, if not centuries, to try to understand what is going on in our systems. Next slide. There's a plethora of different applications you can use hydraulic modeling for. Understanding hydraulics, figuring out cleaning methods, understanding water quality, or even just system optimization. The main things we want to focus on today is looking at fire flow, because using fire hydrants, we can start to understand specifics of sections of pipe. Cleaning methods, is it worthwhile to do different cleaning methods? What's the benefit of those, and what do we learn from them? As well as then looking into transient analysis with surge and understanding what that looks like and understanding the complexities of that. Next slide. There's main categories that you need in a hydraulic model. You need water main information, which determines material and diameter, of course. Ultimately, the material is what impacts the friction coefficient. And then, tank information, pump information. While all these aren't technically related to pipes, they are related to understanding the movement of the water and how different parameters react within the system to understand what that looks like. So all of these are really needed to generate the model and then ultimately move towards the calibration phase. Next slide. I will say in the last 15 years, GIS has been one of the proponents to help increase hydraulic modeling's capabilities. Previously, it used to be very skeletonized, very simplistic models. As with GIS, we're collecting more information. Same way with asset management, CMMS, that more information is being included. You get more detail, right? And as you get more detail, more assets, you're able to then better understand and do different analyses. One of those is looking at inside diameter. That was a key point, right? Obviously, HTP has a smaller inside diameter, but ultimately it has a higher friction coefficient. So while it looks like you're restricting flow, you're actually not, because you're actually able to put as much, if not more flow, because you have less friction to account for the head loss side of things. So capacity-wise, understanding those differences and what those look like. Next slide.
So that geographical information system, it has developed fairly massively. We had a good system in Castleberry when I was there 15 years ago, and Matt, you worked very closely with that. So not only does the hydraulic modeling become an integral part of that tool, but also to send the operators out with a tablet or other things and track the resources and track those assets 2 a.m. when we have that water main break failure. So we're developing that, and the hydraulic model is certainly a part of it. So didn't want to interrupt you too much. Just keep going, Matt. Thanks.
But key point here is if that water main break happened so you've got the hydraulic model, you got the GIS, right? And in the old hydraulic model, if it happened on that loop, you didn't have the infrastructure needed to evaluate why the break happened and really how it impacted the system, right? So now as we get more information, more data, we're able to actually evaluate the entire system, no matter where these events happen. As with GIS, you start and you add more assets and infrastructure, it only makes the model more accurate. Again, garbage in, garbage out. The more information you can put into the calculations, the better the output you're going to get, the more realistic things are going to start to turn. With GIS, we're able to actually overlay the system itself. And you can actually put pumps on actual pumps and get an idea of how the manifold and the tanks all work together to supply the system and what that looks like to ultimately then understand the network as a whole as well. So model construction has taken a big leap with this as well. One of the big key components is obviously demand, right? Whether that's wastewater flow in or providing water network demand out, being able to understand what that looks like. And as you add more assets and infrastructure, being able to delineate where that flow is being added and understood what the impacts are. Obviously, pressure is the key, and being able to understand those hydraulic grade lines and what that looks like. And that's a key valid point, and making sure that we have accurate demands and applied appropriately in the system and network where they need to be done. And that's all part of the calibration phase. Next slide.
Hey, Alan, I've got a quick question for you. One of the questions that came up a couple times so far is, what's the basis for polyethylene C factor being consistent with PVCs?
They're both plastic materials. I'm not sure if Richard or Stephen would like to elaborate in more detail, but they're both plastic materials as they come through there, and that doesn't corrode. So over time, that C factor stays. Stephen, you got something for us?
Yeah, real quick, Alan. So, I mean, that's a good question. So the C factor for polyethylene comes from actual laboratory studies, full flow studies through a polyethylene pipe with fusion joints in the pipe. And then the calculation from that, the pressure drops, things like that, the C factor was actually calculated to be about 160. But we regularly go out with a 155, 150 to 155 as a little bit conservative. And it stays consistent over time. It doesn't, there's nothing tuberculation, there's no corrosion. So it doesn't change and decrease your flow capacity with time as well.
Okay. We also had a question about what types of things can be added to a GIS database. It's all your valve locations, the pipes, change in materials, fittings, We look at actual water demand through the meter reading at that particular moment to give us the actual ongoing daily basis. So we'll cover it a whole lot more. Matt, go ahead and feel free.
Yeah. First is understanding pressure, right? And what are the impacts on that? And a lot of people don't realize that, Florida, it's very flat. You could be in North Carolina or in Texas or out in Colorado where you have a lot of change in terrain, and being able to understand what that looks like. And with that, you get isolation because you have pressure reducing valves at different points in the system to control that. But a higher pressure ultimately leads to increase in joints, wear and tear on joints, wear and tear on valves and fittings and seals on how that works. So being able to drive change in pressure and operate. The issue with that a lot of utilities have is, and Alan, you go to the next slide. With a model, you can figure out where to operate to still meet your minimum compliance, right? And you can figure out what that is. You reduce water loss, but you're also cutting your revenue. You can also revert that to increase your revenue as well and get an idea of what that looks like. But ultimately, the whole point is looking at longer life for your asset, and figuring that out. What's really cool about water quality, and this is looking at an iron-based pipe with a bunch of tuberculation. Water quality allows you to better understand the pipes, and understanding the model and how it works is you might have 8-inch ductile iron pipe throughout the system. And you can see that 8-inch ductile iron pipe gives you a result in one part of the system, but not in a single particular spot. And understanding water quality in a hydraulic model is all about understanding the surface area of the pipe itself. So with plastic pipe, it stays clean. There's no tuberculation. When you start to have tuberculation like this, then the surface area increase, and you'll see that within different sections, now I'm not getting the same result based off my calibration results, and I need to understand why, and you'll see that divergence. The other fact of the tuberculation that adds impacts is obviously reducing your capacity. It increases places for nitrification to take place and hide, impacting other parts of your water quality, and you can get an idea of what that looks like. Once you get this all figured out and get it calibrated, you can see we can accurately predict. We can actually simulate and then actively predict, and you can predict both a clean, smooth pipe as well as a tuberculated pipe and get an idea of how that impacts your system. But again, a lot of diagnostics going into that to understand what are the impacts of a particular pipe section. Next slide. People always ask me all the time, do pipes need clean? Absolutely. It does not matter. Iron obviously has a lot of color, and you're trying to meet that, supply that. And one of the key points here is hydrant flushing, whether it's a unidirectional flushing or just random flushing. When you start taking pressures and you do that amount of flushing in your system, you're going to learn a lot about your system just from the pressure itself. Next slide. Typically, you have to have a known flow, and then with all your other physical parameters and the pressure that you're monitoring, you're able to then understand what that looks like. So next slide. So we've got our diameter of pipe section that we're analyzing. We know what that is. We basically need an upstream and a downstream pressure that those represents as our hydrants. We can also do this in wastewater, and I've got an example of that where you deadhead the pump, and you can look at the pump with its flow rate versus an ARV. But again, we're looking at that pressure drop and to determine it. But the main factor that we're trying to understand here is looking at friction factor and how that pipe is impacted. So we can rearrange the equation. Go ahead and click it next. And we're actually solving for F at this point. And we get an idea of what that looks like on our friction factor. If we need to take it more complex, so we can do the simplicity of with a known flow rate. The problem is when we're dealing with two hydrants, we don't know what the flow rate is. So we have to use a couple other equations, and I'm going to go through these pretty quickly, but this is the engineering side of the presentation. So, basically we're taking 3 different equations, and Alan, you can start to step through these, and you'll follow the colors, and the colors represent where that equation is being placed inside of the next equation to ultimately lead to being able to bring it back to that pressure drop equation where we got it all tied up. We're using all 3 equations to get an idea of really what that friction factor is for that particular pipe. And we don't need to know flow. All we need to know is diameter, the pressure drop, and and the length of pipe with the density of water. Next slide. I will say there's a lot of iron that's left in mains we got a couple other pictures here also where we've got a lot of lining in the ductile iron. But go back one slide. I want to show the sand. That sand is actually from plastic pipe, and during construction, that pipe that was installed, it was only a few years old, or not. It was a few weeks old, few months old. And we can do all the testing and all the sampling and monitoring that we want to do, but ultimately during construction, there is stuff that gets into these pipes and being able to flush those out. And you'd be surprised what can hide inside of that sand inside of a pipe. So it's good to do flushing. Next slide.
Yep, that could be from that over deflection or over displacement of that joint as well, from a PVC standpoint. So,
but again, you can see all and I've seen 2x4s come out. I've seen turtle shells come out. I've seen a lot of different things come out of pipes and start clinking around at the hydrant level, and they end up having to take the pipe off or the hydrant off to get out whatever's in there. So, but it's very interesting to see what comes out of these things when you're doing these programs. But the benefits behind it: cleaning the system, providing a level of maintenance to your customers, as well as understanding the system as a whole, so you can get a better idea of calibration. Next, we're going to look at force main, and this was. So I go back one slide, or one more slide. Go one more click. You can see the divergence. These are actually opposite, but you can see the divergence before the line was actually pigged, and you can see how the model wasn't able to keep up with actual real-world results doing that pressure and flow test. But go back one slide, Alan. Then you can see where it started to line up, where we're able to calibrate at least, and then get to the next stage. So go 2 clicks now. And after we were done pigging, we were able to line it up. When the pipe was clean, we were able to see where the results laid, and you can see the model actually had a really good result. The whole point of these is you can see the model can show you, and you do this by changing your C factors, right? So you might have a tuberculated pipe that has ductile iron could be as low as 80, right? 60 or 80. And you can bring that back up to maybe 110, 120. But that's what I said. Even with the inside and outside diameters, moving to an HDPE plastic pipe like that, you get significant amount of reduction in head loss on your energy grade line, where you're able to increase capacity in the ends. So you can see here you've got the profile view of what that looks like in the different sections. And you can see the grade line on how it works and be able to follow that. And with this, it's really simplistic, where we're just using that very simplistic equation because we know the flow rate this time. We don't have to use Q to try to figure out pressures and all of that. We know because we've deadheaded the pump and we're looking at an ARV downstream and understanding what that looks like on the pressure on the ARV side. Lastly is surge. Surge is one of the very big issue. Nobody really cares about it until it happens, and then everything breaks loose and people are going, well, I don't know what happened. The number one cause of surge is power failure, right? So electricity going out of the facility, even with a transfer switch and a backup generator, you still have 30 seconds before that actual generator kicks on and power is restored, and there is a surge wave going through your system at that time. And being able to understand it and try to mitigate it as much as possible. Pipe material is one of those things. Obviously, adding ARVs, right? You'd be surprised how much an ARV can help. Alan, next slide.
Sure. Oh, this one's really cool. This will help, and I hate to interrupt, help answer some questions we had about water hammer and fatigue. And I was most excited about this. I also have another question to answer after you go through this slide. So keep going, Matt. You're doing great.
Sure. So this is the static version of surge, and you can get an idea. So the blue line's your max. Your green line is your standard operating pressure, and then red is your minimum pressure surge. And this is the result of after you've stabilized it and you got a nice system that's designed. Before that, you would go down to negative 14, right, which is beyond physics. You can't go lower than that. And then you would have something above 300-400 psi on with surge spikes on it. But being able to control, you get an idea. But what this is a simulation, and allows you to see every time you see the black with the little colored splecks that actually represents column separation. And everybody, what a lot of people don't understand is it's not the initial wave that goes out, it's the wave that comes back. ARVs and all the systems are very, very adequately equipped to handle the initial wave going out, but it's the wave that comes back where they can't release the air fast enough, and that's when you get pipe collapse. Because you've got the wave coming back, it can't bring the air in fast enough, and then therefore you get pipe collapse.
So Dusty or Richard, if you want to take some of this, the surge allowance that we mentioned previously of the pipe material design does allow from 200 PSI on a DR11 up to 400, and that occasional surge happens 6 times a day, thereabouts. So this is the scenarios to which we have all pumps on, all pumps off, and we have the greatest demand for that system itself, and then also for recurring surge, that's up to 55 times a day. So for those people that asked that question about fatigue, it's factored into the design, and a lot of the testing that they do at that manufacturing facility takes that into account and runs that pipe material through that fatigue for 11 million plus cycles. So yes, it's certainly pretty robust. We'll get to calibration here in a few minutes. Did you have any more on these slides, Matt?
Yeah, my main point is you're looking at understanding your particular application, right? And you got to understand the constraints and what you're trying to design around, and what makes sense for you, right? Different resources have different applications, and being able to understand that. But a model allows you to test those constraints, understand what they look like, so that you can ultimately make the proper decision on that front and select what you need to select appropriately.
Awesome. So one of the most interesting things about Matt is his willingness to help in any way, shape, or form. So we haven't really worked directly together since my days at Castleberry many years ago, and now Matt's doing something completely different. So he's going to tell you a little bit about what it is that he's doing here, and definitely let us know, because somebody out there's got to have service out there for you.
Yeah. So anytime I get a plug, I'm going to take it, right? So I appreciate that. We are operations and compliance software really wrapped around compliance. So we help utilities full-fledged. We're the only ones that do it across the board, but water, wastewater, MORs, DMRs, cross-connection programs, IPP and FOG programs, helping them manage those compliance issues. But we also have our asset management module, which helps with anything related to field data collection, right? So if you guys, for the consultants out there, if you got any clients that are looking for compliance solutions, feel free to give me a shout. I'd love to talk to you more. If there's any utility operators out there, things on those lines that are looking for something, I'd love to have a conversation with them as well. So thank you. I appreciate the opportunity, guys.
Yeah, Matt helped me out a lot, and he's still helping me out right now. So definitely a great job, Matt, for giving us the basis of how to get that together. One of the questions we had was about compaction of backfill around a pipe, whether or not you could actually put HDPE pipe into a compacted backfill environment. We do have an entire webinar on open cut. It just happens to be timely. We're doing it tomorrow at 2 p.m. as well, but it's also stored on our website at pepipe.org, where you can find that, and then also our YouTube channel. So we do quite a bit of work through here to try to help that educational component. We have well over 60 questions. Keep them rolling. Love that fact. So some of the operational benefits that Matt had talked about are definitely shown here. Pete, you got something you want to share?
Yeah, a great question came by, Alan. I wanted to share it with everyone. And it relates to, what is your metric for a completed model calibration? Do you want to get within X PSI of hydrant flow tests, or is there a different metric for calling your model calibrated?
I absolutely love the question because the next section for us is all on calibration of that hydraulic model, and we'll make sure to be able to address it there. So, what we're looking at now happens to be a live inspection of a metallic water main. It started off as PVC, transitioned to another water main, and we're seeing a liner within that pipe, bituminous liner that's broken apart, and that can encourage that biofilm growth that we eliminate by going with a plastic pipe material type. So there's a lot more benefits of using HDPE, not just for the hydraulic model that you're now learning about, but also corrosion resistance, that soil displacement, since each joint that we fuse together now is as strong, if not stronger, than the pipe itself. And a lot of good things come from using that plastic pipe material. So with that, I'll bring Emily on, and she'll tell you about her experience directly calibrating and using the hydraulic model for the Metropolitan Utilities District. So we'll have the actual real world scenario now. Glad you're here, Emily.
Excellent. Yes, thank you guys very much. Yes, so calibration would be the next step in your hydraulic modeling journey. So after you go through the effort of setting up that hydraulic model, we need to really make sure that it is reflecting reality. So calibration is comparing those observed values to modeled values, and then going through that iterative process. Usually we're combining results and measured values into tables and graphs, and then focusing on areas with large differences to try to really shore up that hydraulic model. Typically, we're addressing those C factors, so that roughness of pipe that we've talked about periodically here, demands of the system, so residential, commercial, industrial demands, making sure that that's reflecting reality. And then QA, QC, so it's just that sanity check, making sure that the data was input correctly. Are those valves showing open or closed? And then the variables, are they assigned correctly? Are you showing a 4-inch pipe and maybe that was supposed to be a 42-inch pipe? So that can have a great impact on your system. Slide. So model calibration, I've defined it just slightly different here, but basically we're just trying to bring that model in alignment with field conditions. So there's a couple of different ways that we would calibrate the model. Would that be hydraulic, maybe looking at water quality, steady state, extended period simulation, or looking at micro calibration. And then there's a really great resource. So AWWA, so American Water Works Association, has a manual of, water supply practices, M32, which can elaborate on all of these calibration practices and hydraulic modeling in general. So if you're interested in learning a little bit more. Hydraulic calibration would be verifying pressures, flows, tank water levels, and making sure that they are accurately simulated in that model. Water quality, we're modeling chlorine residuals and disinfection byproducts. So that requires initial chlorine concentrations, decay curves, and decay coefficients. So it's fairly complex. Steady state, we're modeling the system at a specific moment in time. So looking at maybe a peak hour or a hydrant flow scenario. Extended period simulations, typically we're looking at those steady state models linked together over a period of time. So maybe that's 24 hours and maybe 48 hours. And that extended period simulation is required if we're going to be looking at water quality, because we need to be looking at how that water quality deteriorates over time. So that's part of the requirement there. Then micro or macro calibration. So looking at the entire system from macro, micro, making those fine tuning calibrations. So remember, those field data inputs are not foolproof. They rely on human input and then human action. So, Were those as-built updated correctly? Historical information, maybe it's not as accurate. Maybe we're looking at the wrong section corner. Maybe the hydrants that you tested are not on the same network, which can certainly happen. And then the model also is not foolproof. It was usually updated by humans. So
I'm sorry to interrupt there a little bit, Emily, here, just to
please
let everybody know, we are a 75-minute webinar today. So we are going to 15 past the hour, and we're doing really well. So keep going, Emily. You're doing great.
All right. So a typical way that we would calibrate the system would be looking at these hydrant flow tests. They're a great way to look at the microcalibration and really fine tune that system. So when we have all of that SCADA data input, this is a great way to make sure that it's input correctly. Hydrant flow tests would be looking at a residual and then a flow test hydrant. You can see the schematic there on the corner. We're looking for about a 10 PSI drop at that residual hydrant. We're simulating a fire flow event. So when we do our design, we want to make sure that we don't go below 20 PSI. That may change depending on your authority having jurisdiction. We want to avoid test locations near tanks, pumps, and PRVs. Sometimes those can skew your data and your results. There's also the option to use electronic equipment. If we're getting a flow test on a large diameter pipe, sometimes it can be very hard to accurately measure those tests using manual methods. So to capture that, we would recommend using electronic means and methods. More information can also be found on AWWA M17. It goes through these whole methods for hydrant flow tests. Some of the information Matt had already touched on earlier, but additional information can be found there. So C factors would need to be reviewed and calibrated, especially on historical areas. This is a graphic just showing ductile iron pipe. It's a material that most systems have a lot of. I know we're talking about HDPE here, but just wanted to put this in here to keep in the forefront of our minds. Values can be reasonably estimated based on lifespan. That AWWA M32 has additional information. And most of us may have an idea. We start out maybe near 140 and then degrade shortly thereafter. But the real way to figure out what that C factor is to get the hydrant flow tests. So we would typically, recommend that to just verify. So additional calibration methods would be looking at demand. So there's a couple different demands that you would be running your model on. So we look at the average day demand. So that's the total water used in your system divided just by 365. So pretty straightforward. Maximum day demand, maximum recorded daily demand representing the single highest demand for a given year. And then peak hour demand, the water demand during the hour with the highest system demands. And, demands can go up and down throughout the year. Typically, you're going to see those peaks during the summer, and then the winter months will go a little bit lower. The type of scenario you are running will usually dictate the type of demand that you want to use.
So some of the highest demands that I've seen previously in real life were there during the Super Bowl when everybody's out and about or at other people's houses and using that system itself through that. Or water main breaks, firefighting events, all of those are going to give us some of that peak demand. Isn't that right, Emily?
Yeah, certainly. Yeah. To be a little crass, yeah, we would call it like the super flush. But yeah, oftentimes, during the summer, we'll see high irrigation loads. So oftentimes sprinkler companies will just program those irrigation sprinklers to run Monday, Wednesday, Friday, starting at about, 7 a.m., 6 a.m. So if you drive through any new neighborhood, you may see all of those sprinklers triggering at about the same time. So that can definitely put a large strain on your system. And it can be troubling, certainly, when you're trying to run the system from an operational standpoint. So what does that really mean, bringing that model into real life? So we have a small suburb in the northwest corner of Omaha. This is just a graphic of Omaha. And then to give you an idea of what we're talking about, so that northwest area, they had some pressure issues and some low flow issues. And so we developed a project to try to address that. They were incorporated into the MUD system about 20 years ago. And then prior to joining MUD, they ran on wells. They had some secondary or aesthetic water issues, primarily iron and manganese, I believe. It was before my time. And so the suburbs saw some increased growth, which led to obviously increased demand on that specific pressure zone, especially during peak hours during the summer. So we created a project to try to develop a solution for those low flow and pressure issues they were having. So I've just got a couple of maps here to show that pressure zone, showing the pressure map, and then you can sort of see that zone. So it's that teal color is the specific zone. The area highlighted in the circle on the east or right side of the map is where the specific issues were occurring. On the west or the left side there, areas even in similar elevations had no issues. Likely this was attributed to newer infrastructure. That right side was the older segment of town. So we conducted a few hydrant flow tests to try to calibrate the model and then develop a plan of action and determine a fix.
Great. I hate to interrupt here. Richard, go ahead.
Hi, Emily. I had a great question that came off when calibrating the flow test. How much percentage of error is allowable?
Allowable? I generally try to get it as close as possible. I know that's not a great answer, but I think it just generally depends on what you are trying to model and what you're trying to fix. So we, in this project here, we were replacing a lot of the infrastructure. So we were just trying to get it pretty close. I was able to get it pretty spot on. So once you're able to run those models, there are different calibration methods depending on the software that you're using. So you should be able to get the calibration pretty close. So yeah, and it depends on the calibration method that you are indeed using, whether you're looking at the pump curves or whether you're looking at just the sizing of the pipe. But generally those hydraulic models will allow you to get pretty close.
Thank you very much.
Yeah, so we were able to target this area here highlighted in red. It was specifically older cast iron mains. Some of them were 4-inch in diameter. But those hydro flow tests were really important for us because, as I mentioned before, we took over this area. And so material information, age of the pipe was maybe not exactly known. We estimated it to be installed in about the 1950s, but there's not great historical data for us. So yeah, mains were 1950s era cast iron ranging in 4 to 6 inch. So we targeted that for a pipe bursting project. Some of the areas were open cut as well. Existing sizes were 4 to 6 inch. We did either size for size or one size up. So left no 4 inch for that pipe bursting project. Alan?
Pipe bursting is definitely a proven method for exactly this scenario. We do have an Alliance webinar on pipe bursting, but it's my understanding, I was in Omaha last week, you guys have an internal crew that goes and does some of this work for you. Is that correct, Emily?
Yeah, that's correct. Yeah, we work with both internal and some external crews to help assist us with our pipe bursting projects. So yeah, this project was actually done by our internal crews. So yeah, it worked out pretty great for us.
Awesome. That makes me fairly excited. Rusty Reeves, do you want to come on and because they've got to buy the material somewhere, and we certainly Core and Main provides that opportunity to be able to assist someone like the Metropolitan Utilities District. Isn't that right, Rusty?
Yeah, we definitely, and my focus has been on the no dig style applications here recently. I just think it's going to continue to grow. There's just too many advantages, which I'm sure Emily could attest to. You're not impacting your environment. You're keeping your businesses open. You're making your houses and everything, customers there happy because you're not destroying, maybe old oak trees and everything else. It's just so much more beneficial all the way around. It takes a little bit, I think, the learning curve and people getting comfortable with it. But yeah, we've got 4,000 employees and 450 branches nationwide. We've got 30 polyethylene specific branches. So yeah, any of you out there that have projects want to talk about them, would love to discuss them with you. So. Yeah, I think pipe bursting is very exciting. I know there'll be good presence at the No Dig up in Rhode Island that's coming up in, I believe, April, and we'll have a booth up there as well. I think the Alliance and I know PPI will be there as well. So a lot of resources for anybody interested in it. So.
Great. We've had well over 70 questions and definitely cruising right along. We only have a few more minutes left, but I'm going to get right to the heart of what you got, Emily. We'll give another chance on your camera too, if you wanted to. And then Matt, come on as well. So this slide happens to capture the end result of bursting old cast iron mains and kind of walk us through what's going on here, Emily.
Yeah, so we did conduct those pre-test or, pre-improvement hydrant flow tests to calibrate our model, as I said, and then to just sort of test how the pipe bursting project went to ensure that we were able to deliver a better project and a higher level of service than what those customers currently had. So those initial flows were pretty low, just as we suspected, less than 1,000 GPM there. So yeah, pretty low, and not what we would want. We were able to model that entire project, and we were targeting close to 1,500 to 2,000 GPM for a design target, and we were able to get results that were better than expected, really. So we were pretty happy with it. Just all in all, seeing over 150% increase on those hydrant flow tests.
Am I seeing that right too? It's also 772% increase at Stark Street.
Yeah, so Stark Street was pretty tuberculated. I wasn't on site when they did some of the construction, unfortunately, but yeah, that was one of our lowest hydrant flow tests that I've ever seen, and that some of my coworkers have ever seen. So it was pretty unfortunate, but yeah, we were able to deliver a result that we were all very happy with, to see close to 2,000 GPM at the end of the project there.
So before we get Matt's take on this, because I know he's done this as well, we had a question. How has Omaha handled the surge in demand from summer irrigation cycles? Have you defined when customers can irrigate in order to minimize the impact of the operation on the system?
Yeah, so currently we have not done any restricted watering or anything like that. We did have some projects this last summer. So we had a request for customers to adhere to alternate water scheduling, but we have not implemented anything other than just a general request. It's definitely something that is on our minds from an operational standpoint. I'm sure from many other individuals who operate water systems, because you do certainly see those spikes. As I mentioned before, it's Monday, it's Wednesday, it's Friday, between the hours of 5 a.m. to about 8 a.m. So it's not something that we have implemented to our community and to our customers as of this time.
Okay. Water loss affects everybody all over the country. So we'd like to see a leak-free pipe system with a joint that is as strong, if not stronger, than the pipe itself. Matt, have you seen similar results to post-rehab to remove aging metallic pipes? And tell us about your experience.
Absolutely. And I got to say, I'd be mad if I replaced my shower head before this, because I'm sure it was probably working just fine. And it wasn't the shower head's fault, right? So, but I can only imagine the pressure increase that they got after getting that much more capacity. But yeah, all the time, right? And you're going to see it in different applications and what it looks like. And it's always fun to go through the different systems and understand the root cause, look at the different evaluations, and see what really is the issue causing it. Because it's always never the same thing. There's always something that changes, or there's a elevated tank, right, or an elevated tank that's nearby that may cause things to shift or change, but ultimately it's the same result. So being able to try to understand what are the different, like I said, it's equations, and all you're trying to do is solve and put the different parameters in the equation to help it solve. And you got to really understand the equation to figure out, is this input correct? Is this what other input could be giving me the issue? And being able to bring all that together.
Good. We only have a few more minutes here, but lots was presented. So in general, I've got the agenda for today's topic in front of you. Dusty, you're more than welcome to come back on as we try to capture everything. So we did a little bit on the properties of HDPE. That's part of our 301 section that is available and open to you to learn. Those properties, that viscoelastic behavior, the durability, the ruggedness, the fatigue resistance, those are all good properties that we want to be able to use this pipe material in the field and figure out how to really maximize those installs through trenchless. And a lot of you out in the audience has already recognized how useful it is with trenchless. So then we got into some of the disinformation out there that, with a reduced ID of this pipe diameter, really it's going to have a fairly dramatic impact on how these systems operate. And the theoretical single pipe solution to just look at head loss through that isn't always correct. And we've spent 45 minutes talking about the complexities of how to actually look through a hydraulic model. It's a whole subset different from the pipe people. And that's why Matt and Emily, I'm so gracious to you to share your expertise here with us and tell us the things that you've gone through to be able to develop your model and then use it. And then just that result is the proof in the pudding, in that manner that we're seeing such dramatic improvements in water flow through that pipe. So we only have a few more minutes left. Pete, you got something that you're chomping at the bit to add for us here. So yes, please let us know.
Emily, quick question for you. I'm interested in just your summary of, with all this calibration and all this modeling you've done, the whole ID matching issue that Alan talks about, and that the competitive pipe materials like to say you have to match IDs. What have you found directly as it relates to polyethylene and the other materials? Do you have to match the IDs in your experience?
So when I model, typically I will model using the ID and the specific C factor. So I don't know if that specifically answers your question, but that's typically how I will set up my model.
So the flows that you're seeing with all this work that you've done are typically adequate for MUD.
Yes.
So, Jared, with your agency last week, we spent some time with him. He had mentioned in certain areas that, you know, if you're worried about fire flow, you just go to the 8-inch pipe as opposed to that. The material cost, and this is specifically what he said, is not so much more in that scenario that you'd go to an 8-inch pipe. We also showed early in the presentation that you can go to a DR13.5 in that matter instead of the 11, which is closer matching your actual operating pressure. Richard, you want to add something? We only got about 30 seconds left. I'm so glad to see everybody.
Thomas had a great question. He says, you know, when you have these pressure changes and increases, how do you prepare your clients for that? And then additionally, he said there are water chemistry issues that could affect the high density. And the answer to that is no. You don't have to worry about that. But I can't answer the first part of Thomas's question about how do you prepare your customers for this higher pressure increase?
It's actually not a higher pressure increase. It's a flow increase. And as Matt opined earlier about replacing the shower head, it could be perceived as a pressure increase, but what we're doing simply is increasing the amount of flow that is available and comes through that faucet when we replace that tuberculated pipe. I think I nailed that pretty good. Matt and Emily, thank you so very much for participating. Any final words from either of you?
I was going to say I've seen a pipe swage lined with HDPE and had the same capacity. So I don't think ID really is that big of an issue as long as you're doing it properly. So
cool.
It's all about
Thank you so very much, everybody out there. We adhered to the 75 minutes, and we really appreciate your time. So there will be a survey. Make sure you complete question 4 on the survey if you want your PDH, and then also come join us for other events. We love it. Thank you all very much.
Hey, thanks, everybody. Emily and Matt, thanks so much.
Thank you.